Alrighty, folks. Today we're going to be talking about section 7.3, which is doing the same sampling distribution stuff as we did last section, but instead of doing it for the mean, we're going to be doing it with proportions. Right? So, whereas last time we were talking about having the population mean and figuring out the probability that any given sample has a particular mean based on that. Right, here we're going to be talking about the population proportion, which we call P, and it's always going to be X divided by capital N. And the sample proportion, right, so P is taking the place of our mu, and sample proportion, which we are calling P hat, is taking the place of X bar, right? So mu is or P is going to be doing the same things that mu did before, and P hat is going to be doing the same things that X bar did before. And this is X over little n. X equals the number of individuals with a certain characteristic right? So if you're wondering about the proportion of people who voted in the last presidential election, then X will be the number of individuals who voted in the last presidential election. If you want to know the proportion of people who own a dog, then X is going to be the number of individuals who own a dog, right? If you want to know the proportion of beetles who show up in a certain area of your experiment, then X is going to be the number of beetles that show up in that area of your experiment, right? It's the number of people with a certain characteristic that you care about. N is the size of the population, just like it's always been whenever we've talked about capital N. And little n is going to be the size of the sample, which is what it's always been whenever we've talked about little n in one of our formulas. So if you recall before, last section, we said that we could do all the stuff that we wanted to do. We could find these probabilities if either the population was normal or n was bigger than 30, right? So for these problems, it's a little bit more complicated, right? We need n times p to be greater than or equal to 10. And, not or this time, and we need n times 1 minus p to also be greater than 10. Right? So in order to, for the sampling distribution to be normal, we need both of these to be true. Right? And we really do need it to be normal to answer the probability questions that we have, at least in this class. Right? But if it's going to be normal, we need to know about its mean and its standard deviation. So the mean of p hat, right, is just going to be the population parameter again. Right? That's actually just like we had last time. Right? We said that mu of x bar was just mu. Right? So mu of x bar is equal to the population parameter that we're talking about, right? So here mu of p hat is equal to the population parameter that we're talking about, right? Sigma of p hat is going to be the square root of p times 1 minus p all over n, right? So for any of these probability problems, we have two options. The first option is to find the standard score. right? So that looks like Z equals P hat minus mu of P hat all over sigma P hat, which is, of course, P hat minus P all over the square root of P times 1 minus P over N, right? So, and then once you do that, you take the standard score, you look it up on the table, you find maybe it matches up to here, right? So you look for it on the outside, and the probability is somewhere there on the inside, right? Given by the standard score, right? So that's what you can do anytime you have something normal. The second option is to use your calculator's normal CDF command, right, from the distribution list, and put your lower bounds, your upper bounds, your mu P hat, and then your sigma P hat, which is, of course, we're in a particular situation, so we know that that's, the lower and the upper are always given by the problem, so that stays. But mu of P hat is just P, and sigma P hat is the square root of P times 1 minus P all over N. Right, so you can plug that into your calculator for that command. Right, so let's do some problems. And again, I'm going to have to talk through getting those final ones because I don't have a table I don't have the table you're looking at, and I don't have a working calculator, at least that can give me normal CDF, but we can sort of walk through the process of it. So these are going to be word problems, so I'm not going to try to read them as I'm writing them, because that's just asking for problems. So there'll be a pause here for a moment. That is the weirdest K I've ever drawn. Alrighty, so here we have a problem, a proportion problem specifically, right? Because we have this population and this sample that we're talking about, and we want to know, or we have questions about how many of a particular characteristic are we going to get, right? So for us to answer probability questions about a proportion problem, we need to find N and we need to find P so that we can check whether we even have a normal distribution, right? So N in this case is the number of Skittles that we are asking the question about, so that's 100. And so here, the colors, I meant the original 6 colors, the base Skittles pack. So if they all show up equally, that means that the population proportion, if we look at every Skittle that was ever made, or at least of the original packs, and we look at any given color, specifically red in this case, 1/6 of them are going to be red. Right? So we need 100. Let me lay this out. We want N times P, which is 100 times 1/6, which is approximately 17. That's definitely bigger than 10. And we also want N times 1 minus P, which is 100 times 1 minus 1/6, which is 100 times 6 over 6. Get ourselves a common denominator. And then subtract those fractions. This is going to be approximately 85, which is definitely bigger than 10. All right. Right. Those are way rounded, but not 7 or 75 worth of rounding. That was just doing quick maths. Plugging in your head or plugging it into your calculator, or working out carefully is fine too. But really, the only thing you need to be careful about is it bigger than that 10? So if you do a little bit of rounding, and you're still pretty far away from 10, that's close enough. Right. So the first question, right? So this one is we're asking for what's the probability, right? That's what likelihood means. That our proportion of red ones is going to be less than 10 out of 100. Right? So we have 100 Skittles. We want to know what's the likelihood that we get 10 or fewer of them be red. So that's saying that the proportion is less than 10 out of 100. Right? So if we did option 1, that would be finding the standard score. Z is going to be, let me simplify this real quick before we plug things in. Right? It's going to be 1/10 minus mu p hat over sigma p hat. Whoops, I guess I need to find those, right? So we know that we need our z-score. To find our z-score, we need to know these two things, so we clearly need to know those two things. Mu p hat is easy. It's always just p, so it's 1/6 in this case. Sigma p hat is the square root of p times 1 minus p all over n. So in our case, that's the square root of 1/6. We already figured out that 1 minus p was 5/6 when we did this above. That's another thing about doing these problems is it looks like there's a lot of algebra, but a lot of times once you've done a little bit of algebra for the first part, right, finding 1 minus p is 5/6, we can use that later. Right. So this is going to be the square root of 5. Right? When you're multiplying, or when you're dividing a fraction by a number, that can just become multiplying the denominator by that number. We can simplify radicals like this. And the main reason we'd want to do that in this case is that that's a perfect square down on the bottom. Right? So that means that z here is going to be 1/10 minus 1/6. You know what? I'm going to do this down here. Z is going to be 1/10 minus 1/6 all over square root of 5 divided by 60. Right, dividing by a fraction is multiplying by its reciprocal. So 60 times 10 gets us 6. 60 times 1/6, 60 divided by 10 gets us 6. 60 divided by 6 gets us 10. So we end up with -4 root 5. Right? So now that we have our standard score, we'd want to plug that into our calculator to get a decimal form of it. Then we could look that up on our chart and get our probability here. Right? The other option is to do normal, CDF. We want our lower bound, so we want the stuff that's less than p. We don't actually have one for this problem, so we're going to sub in -infinity, at least as far as our calculator is concerned. We want our upper bound, which is stuff that's bigger than our variable. So that's going to be 1/10. We want our mu, and we want our sigma. Right? We plug that into our calculator, and we get our answer. Right? So the second question was asking the probability that p hat, right, let's look back at it, is more than, right, so we're going to want a greater than sign, 20 out of the 100. So we want to know what's going to happen if it's more than 20 out of 100. So this is asking the probability that p hat is greater than or equal to 1/5. Right, so again, we have two options. We can find our z, which is going to be 1/5 minus 1/6 divided by √5/60. Right, we can do the same sort of multiplication. But we do have to be a little bit careful for choosing this method, right? The probability that p is greater than 1/5. Most tables don't answer greater than questions. They answer less than questions, right? Greater than questions are right-tailed because you're looking at, if you think about that picture, all the stuff on the right of some value. Most tables are left-tailed tables, right? So if we have a standard, a usual sort of table, then we're going to want to translate this to being less than, which we can do using the complement rule, right? So this is going to be 1 minus the probability that z is less than 2/5, right? So then we could look up this number on our table and subtract it from 1, right? So that's our first option. It's a lot less work since we did all this above, right? So this is another case where the fact that we did all that algebra work before means that this problem is a lot simpler, right? So for the second way, we do normal CDF again, right? So our lower bound is something that's less than our variable. So in this case, our lower bound is 1/5. Right? Our upper bound is something bigger than the variable, and there's nothing bigger than the variable in this case, so we replace it with our version of infinity, and then we've got 1/6 and 5, square root of 5/60 again. Right? And we plug that in, and it'd tell us our answer. Right? So there's another, we're going to do one more problem, because there's a type of question that comes up a lot more with proportions than with mean. So again, I'm going to write out a word problem. So it'll be a moment. I can sometimes spell. Sometimes. Okay. So, this is clearly a proportion problem. So in order to make sure we can find probabilities for it, we need to know N and P. Right? You're asking 50 people, so that tells you that your sample size is 50. And this first sentence is about all of their customers, so that tells you that the population proportion is 75%. Right? Which we might use later is the same as 3/4. Right? We can use whichever one of those makes it easier for us. Right? So we need to know that N times P, which is 50 times 75%, 37.5. That's bigger than 10. And we want N times 1 minus P, which is N times 1 minus 75%, which is N times 25%. And that's 12.5. That's also greater than 10. Right? So we can, in fact, do probability problems, which is great. Right? So the question that this is asking is, we want the probability that the population proportion differs, or the sample proportion differs from the population proportion by more than 2%. Right? So if it's less than the population proportion, we want it to be less than 73%. Right? Because that would make it more than 2% away from 75%. Or, if it's greater than, not 75, we want it to be, if it's bigger than 75, then we in fact want it to be bigger than 77, because we want it to be more than 2% away. Right? And specifically when it just says differs from, that means you're going to go the same amount in both directions. So it means if we think back to our normal chart, right, this is 75%, this is 73%, this is 77%, right? These guys are mirrored around 75%, right? So that tells us that this stuff has the same amount as this stuff, right? So these probabilities are going to be the same because these are mirrored, and anytime you have a differs from question, they're going to be mirrored like this. So that means we have three options. That's the right one. Right? The harder work one is to say we want the probability that P hat is less than 73% plus the probability that P hat is greater than 77%. Right? This is going back to way back in the chapter on probability when we learned that OR turns into plus if they're mutually exclusive, and I'm pretty sure that a number can't be less than 73 and more than 77 at the same time. So they're mutually exclusive, so that OR turns into a plus. But we could be clever and say that, well, since the blue and the purple are the blue and the orange are the same thing here, let's just do the orange twice. Right? If the blue and the purple are the same, then just counting the orange twice is the same as counting the orange then the blue. I don't know why I keep saying purple. I apologize. We could also say, well, if the blue and the orange are the same, we could just count the blue twice. Right? And this is part of why it's really nice for everything to be normal, is because we have this nice symmetry property. Right? So if we wanted to do this using the calculator route, which I would recommend, we could do normal CDF. Right, so let's do this one for our answer. What we'd want to do here. I need a little bit more room here. So 2 times the normal CDF. Right, and we want something that's less than our variable, but we don't have anything there. So we're going to replace it with infinity as far as our calculator understands. We want the thing that's more than our variable, so that's 0.73. We want our mean and our standard deviation, so we better figure that out. Mu p hat is going to be p, so it's going to be 75%. Sigma p hat is going to be p times 1 minus p all over 50. This is where I like to use the fractional form specifically. So that means it's going to be the square root of 3/4 1 minus 3/4 all over 50, which is the square root of 3/4 times 1/4 all over 50. Three 3/16 over 50. And like we did before, we can just multiply them. I'm keeping that separate though, because then we can pull out that 16 and simplify it to there. Right, and again, any of these steps, right, any of these steps were something you could have plugged into your calculator and it'll be fine. But since we simplified it that far, might as well plug it in. And that would be what we would get if we wanted to use this method. Right, and it would be similar for this one, and for this one we just have to do 2 different normal CDFs and add them together. Right? Alrighty. So, next time we're going to start talking about confidence intervals, and that's going to be where we start doing the stuff that I talked about at the very beginning of the class, where we realize that it's way too hard to do something for the entire population. So we want to do some stuff with a sample and then see what we can say about the population. So that'll be for next time, and I'll see y'all then.